So we're just going to go over the last few things that need to for this class. One of the few things that we need to talk about is multi-phase flow. That should say multi-phase. Sorry, there's a hole right there. This is multi-phase flow. And what we're talking about is like when you have a D NAPL or an L NAPL and you have water and you have the pure phase. So we call it pure phase is when you have the actual product itself in contact with water. And then we have dissolved phase once it's dissolved into the water, which is what we've been talking about before this point, where we talk about solubility and the KOC and KOFO and all those other things. But what happens when you have pure compound, pure phase of the thing? So we're going to look at the migration of these NAPLs, or non-aqueous phase liquids, and the subsurface is controlled by, and so these pure phase compounds are controlled by the density of the compound. So is it an L NAPL or a D NAPL will impact where it goes. So is it above the water or below the water? The interfacial tension or the surface tension between the NAPL and the fluid filling the pore or the fracture. And so we're going to talk a little bit more about interfacial tensions here and talking about three phases and some of the issues associated with that in a second. And then we also have to deal with the viscosity of it. So how easy is it for it to flow? And this will influence the pump and treat that happens inside of it. Viscosity, so like something like TCE actually has lower viscosity than water. So it flows pretty fast and easy. It's a D NAPL, and then we'll talk about interfacial tensions. So this is really impacting by the property of the rock. So what is the spatial distribution of the pores or the fractures that are inside of the thing? So if we've got a lot of pores inside of there. Some other factors are like the wettability. So we'll talk about that, about wettability in a second here. We'll talk about the capillary fringe or the capillary pressure or capillary pressure. I always say capillary because it's fun. It's kind of like saying your garage instead of garage, and yeah, it's a British way of saying it. So you can say capillary or capillary pressure. And then the antecedent moisture conditions. Is it dry? Is it moist? Is it saturated? This makes how easy it is for it to flow and how far it is down to the water table. So for many contaminant problems and for this course, we assume that the D NAPL migration is rapid, and we're only interested in the final distribution of it. Okay, and so this is the case. We can neglect viscosity of the compound. So we really are just looking at some of these issues associated with this. So we're going to be looking at interfacial tension here. So we're looking at the tension between, say, a liquid A, a liquid B, and a liquid C, and how they, three fluids, so if we have air, water, and a D NAPL together, how are the angles between these different compounds influence it? I may have to stop, and my sunlight is weird right now. Sorry about that. So this is our sigma over here, or our T, which is our interfacial tension here, is at equilibrium when you have them in equilibrium between the three different compounds equals 0. So these three angles all together equals 0, and so we can see that this tension here between A and B is like that, between B and C is like that, and between A and C is like that. When we add up all those angles, it equals to 0 in there. So we measure this in the laboratory. We can look at the between like TCE and water, and that's 5.2 times 10 to the minus 2 newmans per meter, while air and water is 7.2 times 10 to the minus 2 newmans per meter. So the result of the differences in the degrees of attraction for the molecules at the interface. So molecule A is more strongly attracted to each other than they are to molecules B and C in this example up in here. So these molecules want to stay closer to each other than they do want to get closer to B and C compounds into here. And so they want to be sitting into that area there. And so you can measure these interfacial tensions in the laboratory. So one of the big things is what we call wettability. So you've seen this with different types of compounds. I mean, this is like that Rain-X that you get for your windshield wiper. What it does is it makes a non-wetting fluid, so the droplets don't mix into there. So the angle right here is greater than 90 degrees. So this angle right here. Versus if it's less than 90 degrees, it's a wetting fluid, so it spreads out onto there. And so if we have different types of liquid in association with our solid here, here's our A, B, and C things in here. So with respect to a soil, how much of an angle is in there. So we look at the contact angle here. So for wetting fluids, where the sigma is less than 90 degrees, and then for a non-wetting fluid, it's greater than 90. And then so when we're looking at these angles, we're talking about this angle here and this angle here. So those are the angles that we're talking about. And then if something is perfectly wetting, it equals a degree of 0. So we assume the soil water is 0 because it's completely wettable. So it doesn't form any sort of like a droplet on there. We have to make that assumption inside of there. And so it depends on the nature of the liquid and the solid that's in there. And then the following is for typical observations made into there. And so like if you have an air, water, soil system, the wetting fluid is water, which makes sense, and the non-wetting is air. Okay. Now if you have an air, organic, and soil, the organic compounds becomes the wetting and the non-wetting is air. If you have a water, organic, soil, then the water is the wetting and the organic is the non-wetting. And then here we have, if we have air, organic, water, and soil, all of them, we have water is more wetting than the organic versus the air that's in there. And so what we're looking at here is how much does that compound get into it, and this will impact how much it moves. So if it's a non-wetting fluid inside of here, it's harder for it to move and migrate in the system than a wetting fluid. So this is why water is very easy. Wetting fluids that can form wetting onto them move easier than these non-ones, and they form these blobs inside of our system. So when we look at the capillary pressure that's in here, across any curved interface separating two immiscible fluids, there exists a pressure discontinuity known as the capillary pressure. So this is the capillary pressure equation inside of there. And so when we think about this, is like the interfacial tension between the soil, pore, throat, or as a bubble in the wetting fluid. Okay, so when we look at the system in here, so the smaller the radius, the tension, so harder to push something in. So if there's a smaller radius inside of here, and it's harder to push this compound through the system. So it's like inside of a bubble inside of here. So we look at our non-wetting fluid is greater than our wetting fluid. So we assume water is 0 and that the wetting fluid is in perfect wetting for the pore throat for this example inside of here. So the capillary pressure really equals to the sigma that we talked about before divided by the radius of the pore that's inside of there. And that sigma is that wetting fluid over in here. Into that system. And so we can look at the capillary pressure that's being pushing on it. And so this is what's happening inside of your pore throat, is how much pressure is needed in order to push that fluid through there. And so this becomes really important. So for a non-wetting fluid, so this is our air or our NAPL, because if we try to push air into a system, it's actually pretty hard. To enter a water-filled pore, it must overcome that capillary, that entry pressure. So that's our PE, or pressure